like a MO, like a sodium chloride or magnesium oxide, and starting at 0. Starting 0 means is a perfect crystal. It's now creating a vacancy of metal ion, which carry the say divalent cation, so therefore it's creating a 2 minus, and then also creating an oxygen vacancy, and then actually creating a 2 plus. In other words, this is the cation, this is the anion vacancy. If the stoichiometry changes to the say N2O3, like a Al2O3 case, aluminum oxide, and start with the perfect crystal, and then you need to balance the charge. The vacancy of the metal cation is actually, we have a 3 plus, so therefore we have a 3 minus associated with this. And then so therefore, on the other hand, oxygen is a 2 minus, so if you remove the oxygen, what we have left over is a 2 plus. So in order to balance the charge, we have to have a 2 mole of the vacancies, metal vacancies, and then 3 moles of the oxygen vacancy have to be made. And so therefore, a charge has to be found. So you will probably learn about from the specific examples. Okay. On the other hand, the Frenkel defect is instead of removing the ions, plus minus ions, but one of the ions, like a plus ion, to be misplaced in the interstitial cycle, or anion going to the interstitial cycle. So that's just kind of thing. So let's start with the Schottky defect. All right, Schottky defect, NaCl. So NaCl is which one is a larger ion? Sodium and chlorine, obviously. Chlorine, right? Chlorine is about 1.8 angstrom, where the sodium is about 0.9. So it's a very substantially larger and sodium, chlorine, and then sodium is much smaller. And so that kind of ionic compound, the Schottky defect case is chlorine is out, same time sodium is out. And so because both ion is out, it will creating chlorine vacancy and sodium vacancy, but the number of overall stoichiometry unchanged. Okay, you see that? Okay, so this is called the Schottky defect. Now, the interesting part of the Schottky defect is well, how many number of sodium, for example, and chlorine is actually removed? It's not that many. Okay, later I show you this. The enthalpy to make a Schottky defect is something in the order of 2.28 electron volt, which is relatively high. So this means approximately at the room temperature, only 1 out of the 10 to the 15 pairs are missing. So this means that's a very small number, but yet even small, under the higher temperature, the sodium is actually, this is only talking about the sodium. Sodium is seen migrating into the previous sodium phase, so therefore diffusion. Okay? And then if everything is sodium is moving from one side to the other, and then further to the other side, so therefore this is actually creating the sodium is moving. This means the vacancy is moving in opposite direction, and this is the way the ionic conductivity can actually induce. So this means ionic conductivity is either sodium ion or chlorine ion can move. Now, why the sodium is preferentially moved and for the electrical conductivity is because sodium is smaller compared to the chlorine. The chlorine can be susceptible to move in a similarly, the sodium move to the previous sodium place, which is sodium vacancy. If the chlorine is there, the chlorine must also, the chlorine will see another chlorine previous site. However, the chlorine is, I told you, almost twice of the size than sodium. So therefore, which is easier to move, and smaller guy is easier to move. So that's why the sodium is actually a diffusant and to make electrical conductivity, ionic conductivity. So in the size is become in this place why the electrical conductivity is actually happen in this kind of case. Now, if you go into the Frankel defect, the Frankel defect case is overall there is no change in the numbers. And however, in a locally, if in this case, if the let's say original okay, so if the cation is actually moved to the interstitial site, so the cation in the cation place, that's the original place, is creating a vacancy, and then those cation is actually moving into the interstitial site. So therefore, interstitial site is actually carry the 2 plus. Vacancy is the 2 minus. So therefore, charge is balanced. Now, oxygen can be also possible, and oxygen site is creating oxygen vacancy, and then oxygen going to the interstitial site. So the similar things I can ask you, which one do you think is more susceptible for the Frankel defect? Oxygen has a much larger usually in for example, like say oxygen is if you look at the back page of the canister, oxygen ionic radius is 1.4 angstrom, okay, where the cation is probably a lot smaller, something in the order of 1 angstrom or even 0.8 angstrom, something like this. So therefore, if you try to oxygen, if you remove the oxygen, that's okay. But then if you squeezing oxygen in an interstitial site, and this oxygen ion is already large, it's a very difficult to place. So therefore, this is, you can write down in a sublattice condition like this, but it's not going to happen that way. It's more likely in a cation is actually this. Okay. All right, so with that said, okay, the Frankel defect case, and for example, silver chloride is one typical material that undergoes the Frankel defect. So in this diagram clearly shows here the silver, chlorine, silver, and alternatively in a sodium chloride structure or rock salt structures. So the originally silver ion was here. Is now silver ion removed from this site and then placed in the interstitial. So therefore, the number of silver ions, number of chlorine ions remains. So in this case, how you describe the reaction mechanism is, and this is original. This is a let's see. Yeah. So this is a silver ion, and then you creating a vacancy, and then silver ion in the interstitial, and the silver ion is in a silver is actually creating vacancy. So this is a Frankel defect case. All right. So then one of the interesting thought is not one of the application, I would say. These days, all the camera is a digital camera, so probably nobody or probably very few people to use a photography. But have you done photography? And how do you actually? Well, the color is different, but it's like a silver, black and white, and then like a professional camera one still using black point. It's a nice thing. And this case is the film has an emulsion of the silver chloride with a little sensitized dye is actually printed. And then what's happened in the old photograph is silver chloride, or maybe silver bromide, and those kind of silver containing alkaline halide is with sensitizer. The energy diagram is something like this. In the silver bromide as a inorganic material, so therefore the semiconductor valence band and conduction band separated by some barrier internal it's pretty high. Okay. However, if you have some kind of a dye embedded in a film, the photon, in other words, when you take a shutter on, and then the photon comes in, and sensitizer is actually it sends the photon to creating electron hole pair. Okay, and then there's this dye sensitized energy level of basically LUMO level is higher than the conduction power minimum. So therefore, any electron to be excited within the dye sensitizer will actually come to the electron in the conduction band. So this means the reaction-wise, something electron will be captured, then the silver is now basically become negative. Okay, so if it's a silver, it's negative. And then already silver ion is in a silver bromide is actually pretty much ionized, and so therefore silver negative ion and silver positive ion is actually reacting to making a 2 mole of the metal silver. Here's the metal silver, which is a black or non-absorbing species is actually come out. So this is a basis of the photography element. Now, this reaction can be further extended. All right, if you're creating silvers, and then you can have another plus ion, because in silver bromide has a lot of silver ion. It's creating a trimer of the silver, but it's because of the plus is already plus. But with this electron, is reaction, and then trimer with plus will react with another electron, and then we're creating trimer of the neutral trimer. And then you can further go into the cluster is getting larger. So silver 2, silver 3, silver 4, you can increase in. So depending on how much you expose, you have more silver cluster if you want. And so this is the way you can create in a photograph contrast. Okay, so this is basically kind of nanotechnologies. The silver cluster is forming, and then because in all the interstitial silver, which is interstitial site, is the one creating a silver plus. So anything is adding up with a silver minus ion, and then you can have silver clusters, like a neutral silver cluster. That is a visible thing. Okay. So I think this technology is actually infinite. It's old technology, of course, because everybody is using for almost 100 years. But the basis of the technology is coming from this kind of Frenkel defect type science. Okay. Now, if you look at the Frenkel defect in crystallographic wise, okay, so silver chloride or silver bromide is all share the same rock substrate. So rock substructure is just like this. Alternatively, ion is sitting, okay, in like a junction, right? So if you look at the silver, which is described by this black dot. So what is this black dot is surrounded by how many nearest surrounding? Yellow. 1, 2, 3, 4, 5, 6. Which is this site is called octahedral site. Okay. Now, originally the silver is sitting in octahedral site, but now going to the interstitial site. The interstitial site within this kind of a rock substructure is here. And then this rock substructure interstitial site is one of the cube in the center. And then this position is how many, if the silver is actually Frenkel defect to come here, how many nearest surrounding? That is 1, 2, 3, 4, which is tetrahedral. So the octahedral site is now moving to the tetrahedral site. So the size-wise, which one is a larger void? Octahedral versus tetrahedral site. Just looking at it. we can have a fairly large size of the octahedral, but here the tetrahedral site is much smaller. If you go back to the 170 textbook again, okay, I don't remember which chapter is, probably chapter 3, and then take a look at what is the size of the tetrahedral site versus octahedral site. And then if you use those size relationship, and you will understand how easy those octahedral ions can move into the tetrahedral, and that determines the easiness of the Frenkel defect. Okay. So to describing this things, that's all the energies involved, and that's why how much the defect is actually involved is based on the energy of formation. Okay, so roughly speaking, this is the energy of the Frenkel Schottky defect case, and then this is the case of the Frenkel defect. It's varied because of the depends on the materials, and then those are the one is the material specific values, and so therefore we have to look at the database to which one to be likely more the either Frenkel or Schottky, and this number doesn't tell too much. However, if you're going to the using this number and you are able to compute the number of a Schottky defect or number of a Frenkel defect using this number, it's basically you can plug in those enthalpy number to this equation, okay, and then it's divided by the total number and how many fraction of the defect will be formed at given temperature. And obviously, higher the temperature, this number increases. Okay, and then Frenkel defect case is a little complicated because of the well, I think it's given this way, so you can actually again you can plug in those number then at given temperature, and you are able to find out. So the bottom line of this Frenkel or Schottky, which one is favorable, is totally depends on the material structures and also the size of the energy relations. So we have to look at those numbers, and those numbers are usually given at known materials. If it's not known, then we have to basically measure those defects. In this case, is actually you have to test many different cases, either Schottky or Frenkel, or stoichiometry or non-stoichiometry, and all sorts of things. It's a very complicated process you have to go through. Okay. Now, a few more remarks of this sodium chloride, which tends to be, I think this is a typical example of a Schottky defect, which means sodium and chlorine are both are removed, and silver chloride is silver ion is going to the interstitial. Okay, so that's the Frenkel defect case. So the sodium chloride is more ionic than the silver chloride. Can you actually assess this statement? Okay. Sodium chloride and then silver chloride. How do you actually assess whether more ionic or less ionic?
You can use the Pauling electronegativity.
That's right. Pauling electronegativity is a good measure. So using those Pauling electronegativity for the sodium chloride versus silver chloride, and then obviously sodium chloride has a much more ionic than silver. So this is a good measure to which way about that if you have a very ionic, it tends to forming the Schottky defect because you need to remove both and then to stabilize. Where the Frenkel defect case is less ionic, so therefore even one of the cation, anion is because of the size is the large, it is very difficult to put it into the interstitial site, and so therefore usually doesn't happen. So therefore, if you look at the silver case, then even you creating a silver defect here, but silver is actually placed in the interstitial site, although interstitial site tetrahedral is a lot smaller, but still it is stabilized. That's okay. And those things are the one you can actually you can use to, I think it's assessing first approximation. I think it's a good approximation. So if you look at the number of cases, okay, simply compare with those. Magnesium oxide is a pre-ionic, okay, because the group 2 element, the group 6 element. Calcium oxide, lithium fluoride is a group 1,7, lithium chloride 1,7. Okay, so these are the pre-ionic. Now, when you look at the Frankel defect type material, these are also ionic, but still the uranium oxide. And uranium oxide is a rather strange oxide, but the zirconium oxide and calcium difluoride, then strontium difluoride, those kind of things. If you compare with this, and this is a less ionic compared to the Schottky. So therefore, it's tends to form the Frankel defect. Okay. So I think this is a way you can assess to this. All right. So any question at this point on Frankel versus Schottky? It's both stoichiometric, no change in the stoichiometry of the overall, but the mechanism is very different. Okay. Okay. So that's the one type of the defect. The second type of defect is happen, for example, in the silicon carbide. The silicon carbide is it is ionic in a sense because of the silicon carbide located in a different row. So therefore, the electric charge is more toward the carbon compared to the silicons. So therefore, you have some kind of ionic interaction, but more or less these are the one covalent interaction. So therefore, in original carbon side, original silicon side, it can be swapped, and that could happen. So this is called anti-structure disorder or misplaced atoms. Okay? And I think this probably you can easily find out from this formula. But is what's interesting part is if this thing happen, okay, if this is too much ionic, then if you have a cation going to the close to the cation, so therefore these cation are very repulsive. These anions are all repulsive because of the same polarities. So therefore, if the compound are strongly ionic, and this is not going to be happening. However, if this compound is more covalent and less ionic, and then even you creating this kind of a situation, which raise up the total energies. However, it's happen means something's energetically stabilizing this situation. What are they? Is configurational entropies. Entropy is increased. You know, remember the configurational entropy? Configurational entropy is basically how many atoms can be placed in a certain specific site. And so therefore, the entropy part is basically write down S is equal to K log of the specific number of way to placing the atoms in the site. So this S is increased, so that means these are total energies. Total energy is described by the Gibbs free energy is H minus S. So if this one is increased and overall this is decreased, so therefore Gibbs free energy is decreased. You see that? Because this minus sign is quite big in the formula. So this is actually happening in anti-structure disorder or misplaced atom models. So this is all what I want to say in this case. However, I guess Yeah, I think it's probably, again, silicon carbide, titanium carbide, and all kind of things actually happen in this way. Okay. So now I'm going to move into the one of the I think it's important topics called non-stoichiometry. And this non-stoichiometric defect is the big importance on oxide materials. Titanium oxide, vanadium oxide, mangan oxide, all sorts of oxide, it basically undergoes oxygen vacancy or metal vacancies. And then it will actually ending up in never being in the TiO2, but something TiO2 minus X, and something stoichiometric is not preserved. So in a nominal number of the TiX is sometimes it's as low as 0.65 to 1.2. I think TiO2 is probably well known. This is very close to the 2, but still some of the oxygen is missing. And once the oxygen is missing, and this material getting a lot of absorption effect, and then we can see the color change, kind of things. Vanadium oxide is also very interesting material. Mangan oxide is also interesting material, and also so therefore the non-stoichiometric compound is a very engineering interesting and then also the useful, important materials. Okay, so with that said, and I'm gonna work on the very one of the important material called iron oxide. So this iron oxide is forming a U-type structure, similar to the I think you can think about, and this is a rock salt structure. And then there's in the rock salt structure, then you can calculate or you can measure the stoichiometry of the iron oxide. Is very rare to find one-to-one. It's always something like iron 0.95 oxygen. So this means something iron to oxygen ratio is never been 1. Okay. So this means this normally we write the iron 0.95 is looks like iron is missing from this formula, but you can consider, you can write down if you divide it by 0.95, okay, then the oxygen become 1.05. This is a completely equivalent in terms of numbers. So if you look at this way, and this stoichiometry, from this stoichiometry, what we can say is iron vacancy. And if you write this way, and you can say the oxygen excess, right? Now the question is which one is happening when you're creating an oxygen, non-stoichiometric iron oxide. And so this is one of the first interest in iron oxide research. And so then back in 1933, a long time ago, people actually studied of, okay, is this compound usually write down in iron 0.95, is that really the iron vacancies or maybe oxygen excess? We like to find out, okay? And to do so, people done variety of experiment and showing this kind of a database. Okay, so making several compound and to measure the stoichiometry by the experiment, like you can use EDX these days or WXT, and then you are able to find out relatively precisely on iron to oxygen atomic ratios. So when you look at the database, and then you can create those kind of stoichiometry in the lighting wise. So this means is, and also you can measure the lattice constant by the X-ray diffraction, which which is very precisely measured at least 3 or 4 digit number. And the density can be also measured by Archimedes process. And that was one you have done in the 311. Okay, so this is a given data. And what you can find from this data is if the density is increased, it is increased, and then there's an oxygen to ion to oxygen ratio. In other words, this to that 0.9 going to the 0.945, which is increasing. So this is a fact. Okay. So then you may ask, let us find out which is that ion deficient, or in other words, ion vacancies model, or oxygen excess model is likely in non-stoichiometric ion oxide. So which one is actually correct? And this is the question we can raise. So how do we answer these questions? The answer is, and probably you can use one of the compound in the next figures. Okay, this is the same chart that you see here, and I'm going to use the last one. Okay, and if you're making a last compound, ion to oxygen ratio was a 0.945. And then the atomic edge cell constant is determined by the X-ray diffraction, and then density is determined by the 5.728. Okay, so how do we define this? To do so, again, go back to the MSc 170 textbook, and then you can probably go through the how you measure the, how you calculate the density based on atomic structure. Okay, so we can exercise by creating a model, like an ion vacancy model. So in other words, this is the iron oxide crystal structure, and then if you're removing the iron, okay, iron here from here to here, and that is a model. Or another model is an oxygen interstitial model. So here we have a perfect crystal, but it's oxygen, excess oxygen is actually going in somewhere in interstitial. So therefore, this is excess oxygen. How do you can actually verify this? And to do so, density calculation is a very, very useful thing. And then since the density can be measured so accurately these days, and how many digits you can actually measure in your experiment? At least 4 digits, 3 digits, 4 digits, right? And then if you do much more precisely, you could go much sensitive, like a 5 digit. So this number can be easily measured by the Archimedes experiment. But also, if you know the crystal structure, and if you know that is constant, and then you are able to compute. Okay, how you compute? And here's a way to do this. The content of the unit cell is that we have a 4 oxide anion, in other words, 4 oxygens. And then if you assume this model is an ion vacancy, then ion is no longer 1, but 1 minus delta. So therefore, in this stoichiometry, the 4 ions should be in this unit cell, but 0.945 ion. So we know the atomic number for the ions and oxygens, which is 55.86 gram per mole versus 16 gram per mole for the oxygens. And so you're just adding up and then divided by Avogadro number. And then if you further divided by the volume. Volume was coming from here. Okay, so this is a 4.310 is a unit cell, so therefore 4.310 of the cube, and that is actually the volume. So when you calculate this number, the calculated density gives rise to 5.707 gram per cubic centimeter. Okay, so this is one of the calculations. If you do the same thing for the oxygen interstitial model case, okay, how you do this? In this case, we have to consider the oxygen excess. So therefore, the oxygen case is we have 1 divided by 0.945, and that is oxygen's number, more than 1, right? 1.45 or something like that. It's a very small number, but indeed oxygen excess. So the iron is a 4, oxygen is actually slightly excess, and then we similarly multiply the atomic number for the iron, multiply atomic number for the oxygen, and then further divided by Avogadro number, and further divided by the cell constant. And so therefore, when you do so, the calculation indicates 6.039. Okay, we have two different number as a prediction based on this model. Which one is closer to the experiment? Obviously, this one. So therefore, you are able to assign, yes, based on this assessment, the ion vacancy model, in other words, the cation deficiency here, consistent, correct. And so therefore, you are able to write down the compound stoichiometry like iron 0.945. Okay. So this is the way you determine the non-stoichiometric oxygen, because it's stoichiometric there. So in this way, I think what you learned about the MSD 311 in Archimedes method is a very useful thing, and then is how precisely you can measure. And surprisingly, in lots of defect density and defect people are using a density measurement so often, and then actually measure the number of oxygen to lost. Okay? And those kind of things can be directly measured, and then there is no assumption involved. Okay. I have I think it's one of your homework question is asking, I think one of the compound, one of the cases, and you can assume, you can ask, you can do the similar calculation. In this case, whether this is a ion vacancy model is consistent, or oxygen interstitial model is consistent. You evaluate it. Okay. It just follows the same guideline. And see, compare the calculated density from this case, and then compare with the density, and which one is closer. This is the way to do it. Okay? Now, one interesting thing in this interstitial, oxygen models, because iron is now missing. Okay, which means we have a ion is actually located in this position. Okay, and then if its ion is missing, ion could go to cross somewhere in the interstitial site and then go outside of the metals, outside of the material. So therefore, you can, okay, let's skip this one first, and then we can actually look at the visualization first. If the ion FeO case is basically you have iron 2+. The iron 2+ is a size-wise solvent size. Then in this crystal structure, iron located in the center and surrounded by the oxygen, and this is basically octahedral site. 1, 2, 3, 4, 5, 6 in the same distance. Now, iron is basically going to the interstitial site, and then this iron 2+ is too large to be interstitial site. This only way you can actually go into the interstitial site is iron become 3+, and then if so, the ion is actually size is much more shrink, and so therefore this interstitial site is surrounded by the 1, 2, 3, 4, which is tetrahedral site. So therefore, we can possibly creating an ion 2+ and ion 3+ simultaneously within this compound. And that is one of the interesting part of the stoichiometric, non-stoichiometric compound, and especially for the iron oxide can actually vary the valency on the 2 plus and 3 plus, and so the interesting many rich chemistry is coming from that. Okay, so I think the time is up now. I guess probably stop now, and then to come back